I am a software engineer at Stripe. My name is Leela. What is Stripe? So Stripe is a technology company that is trying to solve the problem of building and running an internet business anywhere in the world using technology. And the bread and butter of our product is the ability for online businesses to accept payments very easily through extremely developer-friendly APIs. And we offer a bunch of other tools that are related to the internet business space, but my work ties in directly to accepting payments. Now, with that in mind, what exactly is credit card fraud? So let's use a hypothetical example to try and understand this. So let's say a fraudster steals your credit card information somehow. And the most common cause of this would be a data breach. For example, the big Target data breach from about 5 years ago, ton of compromised credit cards. And people can buy these credit cards for a few bucks somewhere on the dark web. So someone has stolen your credit card number. They buy some expensive item online. For our example, let's say they buy a really expensive watch, like a Rolex, online using your card. They then resell this item on some anonymized marketplace, such as Craigslist. They usually sell it for less than they bought it for, but they didn't actually pay for it, so it's all profit. A few days later, you're looking at your credit card statement, and you're like, I did not buy a Rolex. And so at that point, you initiate what is called a dispute or a chargeback with your bank for this watch you didn't purchase. And you might have seen, you can't really see this here, but there's usually a dispute charge button if you log in to your bank account online. So why do Stripe's merchants, because our merchants are the online businesses, in this case, the website selling the watch, why do they care about fraud? Because it wasn't their credit card that was stolen, right? So the way things work, if I dispute this charge with my bank, let's say I initiate a dispute with Chase, and the bank decides that, yes, this transaction truly was fraudulent, and Leela is not on the hook for this, the merchant, the watch seller, is actually on the hook for the cost of that item. And the literal cost of fraud is the value of the stolen item plus some dispute fees. And so you can imagine that if fraudsters realize that a certain merchant has very poor protections in place and decide to hammer them, the merchant can end up losing a lot of money. And globally, in 2018, fraud losses through credit card fraud is estimated to be about $20 billion. So this is a huge, huge market. So with that in mind, there are three major challenges that we have encountered at Stripe while dealing with credit card fraud. So the first is that it's not always obvious to everyone what fraud means. The example I just presented with someone stealing your credit card number and buying something illegally, that's pretty cut and dry as this was fraud. There are some more gray area types of fraud. One example is subscriptions fraud, where you repeatedly sign up for a free trial of a service like Blue Apron. And after the month, you get your free meals, and then you just cancel, and then you sign up again using a different account because you don't want to pay for the actual service. That's called subscription fraud. There are other types of fraud, such as friendly fraud, where someone buys an item, and they meant to buy the item, but they just don't recognize what the statement description means. They don't recognize the merchant name, so they say this is fraud. And they're not actually ill-intentioned. They just literally are confused about the fact that they made this purchase. So you can get into conversations with people where they might have different ideas for what fraud means, and you might not always be on the same page. Second, no matter how you define fraud, whether or not you include subscription fraud, friendly fraud, all that kind of stuff, the vast majority of charges are not fraud. The bulk of transactions happening on the internet are made by legitimate, well-meaning customers who are genuinely buying that good or service with their own credit card. And finally, when merchants are victims of fraud, they aren't always experts at evaluating the business impact of fraud. So what does that mean? So when you're hit with fraud, remember, you're on the hook for the cost of this fraud. And so a lot of merchants have strong emotional reactions to this because they're paying for these things that were fraudulently obtained, even though they had nothing to do with the person's credit card number being stolen. And so when you actually look at how fraud impacts merchants' bottom lines, it's not always obvious that merchants are considering it the same way we do, where a knee-jerk reaction when you're faced with fraud for the first time might be, I should just block all charges. That's probably not the smartest decision for your business because then you won't actually do any business. But you will succeed in not having any fraud. So it's always a tricky balance to figure out exactly what the objective business impact of fraud is and to try and separate that from the emotional impact of fraud. So how have these challenges translated into problems for our machine learning? So it's not always easy to agree on ground truth for what fraud means. You need to have labels for your data if you're training a model to detect fraud. And you need to agree on some kind of definition for fraud before you can have labels that are meaningful. Most charges are not fraudulent means that there is massive class imbalance in your training data. And since most merchants aren't experts at evaluating the true impact of fraud, whereas we actually want to measure how our models are affecting their fraud situation, ideally by reducing their fraud, we need to have some sort of production evaluation techniques to figure out how well our models are doing. So let's dive into each of these one by one. Effective labeling of data. So when we choose labels, our model is a binary classifier. We just care about when it looks at a transaction, it needs to tell us whether that transaction is fraud or not fraud. And tangentially, it is also important for whatever labels we choose for fraud versus not fraud to be obtainable via whatever production evaluation technique we're using. Because if you want to be able to evaluate how well your model is doing in production, you need to be able to see what those labels are in production. It sounds obvious, but it's worth reiterating. And specifically at Stripe, we need these labels for fraud or not fraud to have the same meaning across all our merchants. If we define fraud in a certain way for one merchant and in a different way for another merchant, that doesn't really help us when we want to evaluate how well we're doing overall across all our merchants. So we need our labels to conform to these three major criteria. So what could we use as labels? So for all of our models that are trying to detect whether or not a transaction is fraud, so using my watch example where a customer files a chargeback with their bank for a fraudulent transaction, that one is pretty obviously fraud no matter who the merchant is, no matter who the customer is, no matter who the bank is. Similarly, there's a concept called issuer fraud records, which are frequently precursors to chargebacks, where the bank or the card network sees this charge, and they realize that there's something very sketchy about this, and they send Stripe an issuer fraud record that's kind of like a premonition of fraud. And a large percentage of transactions that receive these issuer fraud records actually end up getting disputed as fraud by the cardholder. And so you might have heard of TC40s, that's Visa's specific version of issuer fraud records, but MasterCard, Amex, they also have their own versions. So for very specific models that are meant for single merchants, if the merchant tells us that a certain customer is a known bad customer where they've had repeated bad interactions with them, and they want to label this customer as fraudulent, we could use that for a model that is very specific to that merchant. There's a subtle difference here. If we're training a model that works across multiple merchants, and this one merchant tells us that they don't like a specific customer, it isn't fair for us to bias other merchants' labels with this merchant's judgment. So this would only work in the case where the model is very specific to a specific merchant. And some examples that are not good for any of our models, regardless of whether they're for one merchant or for many merchants. So if a customer returns a product, where let's say you order some clothes online, the clothes don't fit, so you send them back. That might be annoying for the merchant, but that's not actually fraudulent. Similarly, if a certain merchant on Stripe decides to just block all charges from some country because they had a bad experience with that country or they noticed that they had an elevated rate of fraud from that country, that doesn't mean that Stripe is suddenly going to label all charges from that country as fraud, because that's an unfair judgment that we're imposing on charges from that country. So at the end of the day, for us, labels depend on our target audience, which more directly ties into what I was saying about how if we want to use merchant-specific judgments, that merchant has to be the target audience of the model. Ultimately, we're trying to optimize for the revenue of our merchants relative to what they'd have without our models. And this means that we want our models to block charges that they consider fraudulent in such a way that merchants are not going to be on the hook for truly fraudulent charges. We specifically, for this reason, use labels such as the chargeback being filed with the bank or the issuer fraud record, because these are actually correlated with true fraud that impacts your bottom line. We don't use labels that are correlated with the perception of fraud, which kind of ties into the emotional aspect of fraud. We could use different labels if our goal was to maintain emotional happiness for our merchants, but that's not what we're going after with our models. We want to actually help your bottom line. And so it's always important to keep that in mind when we choose our labels. Second, handling class imbalance. So before I dive into class imbalance specifically, I have a couple of examples to illustrate the relationship between precision, recall, and FPR. And okay, you can see most of the slide. So let's say we have a model that scores transactions between 0 and 100. And our current policy here is if the score is greater than or equal to 90, we're going to block the transaction because we think that means it's fraud. So if we want to calculate precision, recall, and FPR on this set of outcomes, what is precision in this case? So there was one charge that the model said was fraud, which is transaction 6. That one was actually fraud, so our precision is 1 out of 1, which is 1. What is recall? There are 2 fraudulent transactions in the data set, number 5 and number 6. Out of those 2, the model only correctly detected number 6 as fraud, so our recall is 1 over 2, which is 0.5. And what is FPR? So there were 4 transactions that were not fraudulent, 1, 2, 3, and 4. Our model correctly said that none of those were fraudulent, so our FPR is 0 out of 4 because we didn't incorrectly label a good transaction as fraud, and so our FPR is 0, which is great. Now, taking the same data, if we instead change our model's policy to block if the score is greater than or equal to 30, all our metric values change. So now, for precision, our model has said 3 transactions are fraud, 4, 5, and 6. Only 2 of those are actually fraud, numbers 5 and 6. So now our precision is 2/3, which is not the same as the 1 we had in the previous example. Recall, on the other hand, there were 2 fraudulent transactions, number 5 and 6. The model correctly said that both of those were fraudulent. So now our recall is 2 over 2, or 1.0, which is much better than last time. Last time it was just 0.5. And FPR now, we have 4 truly non-fraudulent transactions. Unfortunately, our model mistakenly said one of those was fraud, number 4. So our FPR is 1 over 4. So just by changing the threshold at which we are blocking transactions, we've completely changed the values of these metrics, although the underlying model actually hasn't changed. Now, with that in mind, let's talk about class imbalance. So as I mentioned a little while ago, very few transactions that we see are actually fraudulent. This is less than 1%. So it means that more than 99% of transactions are legitimate and made in good faith. However, it also turns out that model performance is better when you train on a more balanced data set. And as proof of that, you can mostly see these. The precision recall curve on the left was obtained by training on a very imbalanced data set, and it looks really bad. It kind of dips, and it never really comes up. It flattens. I have that on another slide. I'll pull it up again. And the one on the right is a more normal-looking precision recall curve, and that one was obtained on a more balanced data set. So why does this happen? So our model produces a score for every charge between 0 and 100. Our policy is that since our model is a binary classifier, where we ultimately need to say block or don't block, we pick a threshold between 0 and 100 at which we decide to block or not block. And basically the way that works is you pick your threshold. If the score for that transaction is greater than or equal to the threshold, you block the charge. If it is less than that, you allow it. And we picked this threshold in general to maximize recall while capping FPR. Now, why does that make sense? Our ultimate goal is to maximize revenue of our merchants and to optimize fraud blocking for that. I could, in theory, block every single charge, and you'd have a recall of 1, and you'd never experience fraud. But then your FPR would be off the charts because, remember, 99% of transactions are not fraud, so I've just ended up blocking a lot of good charges simply to have a recall of 1. By maximizing recall while capping FPR, I'm maximizing the amount of fraud the model is blocking for you, but also not hurting good customers by wrongly blocking their well-intentioned transactions. And so let's say our validation set has very few fraudulent charges relative to non-fraudulent charges. So the validation set is extremely imbalanced. So given the definition of FPR, which is false positives or false positives plus true negatives, and so false positives is legitimate transactions that the model has incorrectly said were fraud. True negatives are legitimate transactions that the model correctly said were legitimate and didn't block. If your validation set is very imbalanced, you can get a lot of charges classified wrong. You can classify a lot of good charges wrong and still have a relatively low FPR because the true negatives part of the denominator in FPR is really, really large. And what this ends up resulting in is you pick a very low threshold on a 0 to 100 scale. And this results in very high recall, but very low precision. And you can sort of see what's happening in this precision recall curve, which is the same one that was cut off a little while ago, where very quickly, recall is doing well, but precision has just fallen off a cliff. So this all sounds good, but there's a slight hitch. When we train our model on a balanced data set, we end up with balanced validation data. And we're picking our optimal block threshold such that we optimize performance on the validation data. However, we ultimately run our model in production. Production is not balanced data. Production still has only 1% fraud in it. There's no way for me to morph production data such that it is balanced because that's not how the real world works, unfortunately. So ultimately, when you are trying to figure out how to set up class balance for training, it's not always obvious that the class balance that works best in validation will be the same one that works best against imbalanced production data. What we've generally found to be true is that imbalanced training data does not do the best on either validation or evaluation data, but the class balance you use, the one that is optimal on production data might not be the most optimal one on validation data. So it's important to make sure you're looking at both. So what did we end up doing? So we decided to run a set of experiments to determine the optimal target rate for fraudulent transactions in our training data set. What do I mean by target rate? So we basically tried out different percentages where we said that we wanted our training data set to be X% fraud and 100 minus X% non-fraud. And we tried out different values of X. We plotted different ROC curves, and it's a little bit blurry, but one of them ended up working out the best. The way we make this happen is we keep all the fraudulent transactions we can get our hands on, because fraud is really rare. And we downsample the non-fraudulent transactions as needed, such that we can obtain that target rate for fraud in the training data set. So to use some concrete numbers to explain this, let's say we have a data set which has 1,000 charges. Out of those, 10 of them are fraud, 990 are not fraud. And let's say in our experiments, we determined that the best target rate in training data is 10%, which means that 10% of your training data has to be fraudulent charges. So in this example, what we would do is we would keep all those 10 fraudulent charges in the training data, and we would only keep 90 of the non-fraudulent charges in the training data. We would literally discard 900 of the non-fraudulent charges. And this seems counterintuitive, but I trust experiments, and experiments proved that this worked best. So the final lesson and takeaway for us is around having a good production evaluation technique for your model. So I'll get to what the counterfactual part of this means in a little bit, but let's talk about why you need a production model evaluation technique. So if you look at this diagram, I'm not sure how clear it is for you guys, but if you look at the universe of all charges our model sees, true positives in the case of our model are fraudulent transactions that the model has correctly identified as fraudulent and ends up blocking. False positives are legitimate transactions that the model wrongly thought were fraudulent and therefore wrongly blocked. This is straightforward, but if your model blocks a charge in production because it thinks this charge is fraudulent, how do you know that the model got it right? So the way we determine if a charge is fraudulent or not is the charge goes through, and some days or weeks later, we see this chargeback being initiated via the customer whose card was used through their bank's website. But if we think a charge is fraudulent and we block it because we think it's fraudulent, we haven't let the charge go through to see if there's going to be this chargeback filed by the customer. So how do we actually know if we were correct in determining that this was fraud? Similarly, if we blocked something because we thought it was fraud, how do we know we got it wrong? How do we know that this wasn't actually going to end up being fraud? We're basically biasing the outcomes of our charges using our model. So we need some way to estimate unbiased data for true and false positives, because we need to have these numbers to calculate precision and recall in production. We can very easily calculate these numbers on validation data because that is historical data. But if I want to actually figure out how well my model is doing in production, I need some way to estimate true and false positives in production. So counterfactual evaluation is the solution here. And what that means is that it's a technique that helps us measure what would have happened to a transaction if our machine learning model had not intervened and blocked it. So it's how we're going to estimate what would have happened in the absence of the model. And there are two primary motivators here. The first is we need to estimate true and false positives to figure out how well our model is doing in production, because you need to have an estimate of true and false positives to calculate precision, recall, FBR, whatever your favorite metrics are. The second reason, which might not be as intuitive, is that this is the same way we generate unbiased training data. Why is that true? So our model in production is blocking and allowing transactions. We can ultimately only train on the transactions that we have labels of fraud and not fraud for. And this means we can only train on transactions that the model has allowed to go through and hit the card network, because those are the only ones we can observe the true outcomes of. For the ones that the model has blocked, we have no idea what's happening to those, because the model blocked them and hasn't let them go through to the network to see what ultimately happens. But our model is still blocking transactions that thinks are fraud, right? So the model is blocking most things that it thinks are fraud. And out of all the transactions that the model lets through, the bulk are not fraud, because there's a reason why the model didn't block them. So the only fraud that we end up seeing with true labels is the fraud that the model could not catch and therefore let through. So this means that the fraudulent transactions that we have true outcomes for are the hardest fraud, because the model could not catch them. That's why it let them through. And what ends up happening is that if you literally just use these transactions that you had labels for because the model let them through, over time, the model forgets what easy fraud looks like, because you keep training it on only the really hard fraud that it let through because it couldn't catch. And over time, it just doesn't know what normal or easy fraud looks like and ends up not being able to catch it. And so we need some way to obtain labels for some of the more easy fraud that the model would have blocked, so that we can use these in training to keep our model more effective. And this is a real problem. So the ROC curve on the left was when we first trained the model. It was doing great. And then the curve on the right, which is a lot worse, was after the model forgot what easy fraud looked like, because we just kept training it on the really, really hard fraud. So how do we set up our counterfactual evaluation framework to solve these two issues? So the first attempt that we tried, we took a small percentage of the transactions that the model would have blocked, and we reversed the decision to block them and actually let them go through instead. And we used a propensity function to determine the probability of allowing that transaction. So if you look at this chart here, we have this model that hypothetically blocks if the score was greater than 60. So for all transactions with a score of less than 60, probability of allowing is 1, because the model is not going to block anything that has a score of less than 60. For scores between 60 and 100, there's a decreasing probability of letting that transaction through. And as you might have observed, the probability of allowing it is inversely proportional to how high the score is. The goal was you don't want to let through as many of the most fraudulent transactions, which would ideally have a score closer to 100, compared to the least fraudulent transactions. And this way, we let through some amount of the more normal fraud, which is between 60 and 100, to obtain true outcomes on those transactions. So how do we evaluate model performance using these? We would only look at transactions that were allowed by the model, because those are the only transactions for which we have outcomes. But now, in addition to all the transactions that the model was previously letting through, which are legitimate transactions and the really hard fraud it couldn't catch, we're also letting through some of the more normal fraud that the model is correctly detecting as fraud, but we are consciously reversing the decision to block them. We would then upweight each transaction that the model allowed by 1 over PLO. So if the model was going to allow this transaction all along, if the score was less than 60, this weight was going to be 1. But if the model was going to block this transaction, and it had a 0.1 probability of being reversed, now we are allowing, if we end up allowing that transaction, it gets upweighted by 1 over 0.1, which is 10. And we would use these weights in both training and evaluation. And as an example, as anyone who's used scikit-learn is probably aware, you can use sample weights really easily when calculating precision and recall. And the sample weight equals weight is these weights that were 1 over PLL. And just as an example of how this looked, so let's say that our model had a default policy to block if the score was greater than or equal to 80. The two transactions that the model would have blocked, number 3 and 4, had scores of 80 and 90. And given the P allows for them, they have weights of 5 and 10. So of those two, we ended up allowing both of those to see the true outcomes. The model would have only blocked transaction 4, out of the 2 transactions, the only one that the model would have blocked that ended up actually being fraud was transaction 4. Transaction 3 would have been blocked, but the true outcome was that it was not fraud. So our precision is 10 over 10 plus 5, which is 10 over 15, or 2/3. For recall, transactions 2 and 4 are truly fraud when we obtain their outcomes. Out of those, we would have only blocked transaction 4. Transaction 2 was allowed. So the recall is 10 over 10 plus 1, which is 10 over 11, or about 0.91. So this all sounds great, but we found some issues here. These weights, the 1 over p allow, had a lot of variance and noise. And this ended up having results, this ended up causing variance when we were estimating precision and recall using these weights. A single transaction with a high weight that we got wrong could shift the estimates significantly. So what does this mean? Let's say we had 10 fraudulent transactions, and one of those was a transaction that we reversed, and it had a p allow of 0.1. Actually, let's say 0.01. It was like a really, really fraudy transaction in the eyes of the model, and we reverse it with a probability of 0.01, so now it has a weight of 100. And if we got this transaction wrong, the weight of 100 far supersedes the weights of the other 9 transactions, which are all significantly lower, and that would just end up really shifting the values of precision and recall. Secondly, the calculation of p allow was not as straightforward as it sounds. When we designed that propensity function with the inverse probability of reversal, the function assumed that all events it was fed to calculate p allow for were independent events. But what does that mean for us? Does this mean the events should be user sessions, where each user session is an independent event? Should it be each individual transaction? How do you deal with people who are repeatedly retrying the same transaction, where let's say the first time they try to make the transaction, but there's a typo in how they entered their name or their CVC, and then the next time they try again and they get it right? Like, should both those have the same probability? Because the way the function works, it deterministically generates the same p allow for every event, but you need to actually have confidence in the independence of your events for this to work. And we didn't really have confidence at the end of the day. So we tried something new, and this is what we do today. For a small percentage of transactions, we score the transaction using our model. The model produces a 0 to 100 score, as always. And no matter what the score is, if you are in that X%, the transaction is allowed. So this ends up meaning that all transactions that the model would have blocked, so all transactions between 60 and 100 for scores, all now have a uniform probability of reversal. It also means that all transactions, regardless of score, have a uniform probability of reversal. But it doesn't really matter if you were going to let through that transaction anyway. And if you look at the propensity function now, it's much simpler. If we were not going to block the charge, we're still not going to block the charge. And any charge that we were going to block, I've used a hypothetical 0.1 p allow for all transactions we were going to block. And all transactions in this X% that we call our holdback group get uniformly upweighted instead of having this variance in the upweighting, because p allow is now constant. Why does this work better for us? We now are not dealing with any sort of variance in our weights. Because we have a uniform p allow, we have uniform weights. And this means that we aren't having a single high weight transaction bias the estimators for our metrics. And we aren't overestimating or underestimating metrics because of the lack of variance. The X%, the holdback group, is a uniform subsample of all transactions. And so we consider this group to uniformly represent our entire world, and we can calculate true precision and recall since it's a uniform subsample. Ultimately, the reason why we like this method a lot more is that we got rid of variance in our estimator function, and as a result of that, we have much more confidence in the actual estimates the function is producing. And since we also use these weights in training, the good news is that our precision recall curves ended up looking mostly the same. So switching to this method of uniform weights did not actually have a negative impact on training either. So what are our takeaways here? First is that when you're labeling your data for your model to train on and evaluate on, the appropriate label to use depends on what problem you're trying to optimize for, which in our case was revenue maximization. If we wanted to optimize for emotional happiness, we'd probably need different labels. Also, the labels you used depend on the context and scope of the problem, where if you want to apply specific judgments to specific groups of targets, you need to make sure that your model is very tailored to that group. Secondly, aiming for a constant target rate in the training data for the positive class, which is fraud in our case, rather than a fixed downsampling rate for the negative class, which is the non-fraud, results in the best long-term class balance and model performance for us. The problem with fixing the subsampling rate for the negative class is that if your data is growing over time in volume, then it will end up varying the target rate for the positive class. And at least for us, we found that this was an issue because the number of transactions we were processing was growing year over year. So fixing the target rate worked out much better than fixing the downsampling rate. And thirdly, you need a counterfactual evaluation strategy that works so that you can evaluate how well your model is doing in production, and that is also statistically sound so that you actually trust the estimates that it is producing for you. Thank you for listening, and I would love to answer any questions.
Thanks for the great talk. So you mentioned how you sometimes let fraudulent transactions go through, even though your model thinks it's fraud. And so basically, I mean, this is really great for the long term because it allows you to build great models in the long term, but it could potentially hurt a merchant in the short term. So, and you're publicly saying that you're doing this. So do you think like there might be a case where a merchant accuses you of saying, hey, like, why did you let this fraudulent, I mean, they probably don't know like what's going on with your model, but do you think you could ever be like accused for not preventing harm that could have been prevented?
So we're actually super open about the fact that we do this. It's in our terms of service, it's in our documentation, and we're very explicit that doing this results in optimal model performance for that forgetting fraud reason. I use 10% as a hypothetical number. We're not letting through 10% of things we would have blocked. We've found that the number, we've basically optimized for the minimum number we can let through without actually having any sort of meaningful impact. But there's also a trade-off, right, where I can make you a much worse model without doing this. And people are pretty receptive to that, where they understand the trade-offs between the two. But yeah, we're not trying to be shady about it. Like, we're pretty explicit about why we do it. And if there were a way to have our models do really well without doing it, we'd totally do that. But that way did not work. So this is where we're at. Yeah.
Question, GDPRS and the right to be forgotten. How do we handle that? So
this does not really involve any PII. So it doesn't touch GDPR. Like, GDPR for us involves like personal information, personally identifiable information on each transaction. These functions don't deal with any personally identifiable information. Like, when we're choosing events, we're not using any information about the consumer to choose what the PLL for that event is.
So the data itself doesn't have any?
No. Like, the function does not actually care about the contents of the data.
So
I actually didn't understand in the talk, like when you train when you basically subsample the training set, then try to build a model on the validation set. Like when you test the validation set, it still basically performs good, but in production it's actually the unbalanced data. So did you ever try one-class classification methods?
What do you mean by one-class classification?
This kind of problem is very common in literature, in computer science literature, which is called one-class classification, actually. So because it's totally an unbalanced set, you're trying to figure out what are the fraudsters. And you don't know among the population which is the fraud population, like which transaction is the fraud population.
But we actually know which ones are fraud, because we only train on transactions we have the labels for.
Oh, no, I get that, but there are, among all the transactions coming, you don't know which one is fraud.
In production.
In production.
Right.
Yeah. So that is what is called the one-class classification. Like, mostly they use support vector machines, and that means one of the techniques which is used.
I'm not sure I understand what this...
No, what I'm saying is that you basically do a binary classification, basically. So which are the techniques you applied in that?
In binary classification?
Yeah, the actual models which you tried.
Like, what is the model we use?
Yeah.
We use gradient boosted trees.
Oh, okay, okay. Okay, got it. Okay, that's all.
Hi. So you train your model is offline training or online training? And the follow-up question is how often do you update your models?
So the first question, do we do offline or online? We do offline. And the second is we are constantly retraining every few days, yeah.
Thanks for this talk. It was eye-opening for me. I loved some of your slang. The word fraudy is like my new favorite word. And I want to know some other Stripe slang. Can you give me some other stuff?
I think I just made up fraudy. I don't think I've gotten it to catch on. We don't have a lot of other fraud slang. We have a weird internal language, but that's unfortunately not at the level of fraudy.
I had one question as well. You say you're holding out a certain percentage, I assume a very low number, right? How do you know that that's not itself biased? Do you just do it randomly, or how do you pick the sample?
Yeah, we have a randomization function based on our definition of independent event. And so we do a random X% of that event.
Is it a uniform
Yes, it's uniform, yeah.
In relation to the model freshness, I was curious, if you guys ran a model historically that performed really well, have you tried using the data set that you trained on and push that forward into the new data set that you would train on a month or so later?
So is our training window sort of sliding forward?
No. Essentially, you trained a good model, it performed really well. So it's you kind of can assume that the fraud events that happened in that training set were good. Mm-hmm. Could you not also just maintain that data set, add it into the new one that you train the model on a month later to have it re-see that same stuff?
So that sort of ties into the optimal length of the training window and the amount of data you feed it. And I can give you a whole other talk about that. But ultimately, what we realized is the nature of fraud changes very quickly, and who the victims of fraud are change quickly. So using stale data is not always the right move.
We have time for 2 more questions, I think.
So I'm aware of card issuers having their own models for detecting fraud as well. Does that happen before or after your process? And follow up, how does that affect your model and your data, how you train and how you evaluate your results?
So that happens after us, where so first when we see a transaction, it goes through Stripe, and we'll apply our model on it. If our model does not block it, it then goes to the network, and that's where the card issuer's model would run. And what this means is if we let through a transaction and then the issuer decides to block it, then again, we can't use that in trading for the same reason that we don't actually get to see the labels. And yeah, but the issuer probably has a good reason for blocking it as well, and they're completely independent, where we can't influence what they do. So we just happen to be upstream of it.
So we've noticed that fraudsters also forget what their old tactics were. So you put up a net, you catch a bunch of tuna, all the tuna leaves, you catch nothing but dolphins, you take the net down, the tuna come back. So when you have these holdout populations, do you find oddities like that where only the good users that keep running into the wall are still hitting those blocks? All the fraudsters figure out I get blocked every time, so they go to greener pastures, and then does that iterate back and forth? Because we've noticed, like, put the wall up, the fraudsters go away, take it down, the fraudsters figures back up, we can put it up, so we can almost recycle our rules, be like, oh, it's like a seasonal thing, because they forget too. Have you seen anything like that as well?
Not in as nice a pattern as you're describing, but we generally try to have features that try and have memory, where it's like your training data isn't necessarily looking at really old transactions, but if you have features that incorporate history into their values, we've found that that has helped. I don't know if that specifically answers what you're asking for, but I'm happy to chat more. Yeah.
Okay, we're a little short of time, so if you have additional questions, you could ask Leela. Please meet with her. We have a lightning talk starting in 10 minutes. I think it's downstairs in the ballroom. Let's please give Leela a hand for her excellent talk today. Thank you.